In the late 1800s, copper was the leading industry in Montana. With the demand for copper wire growing very fast, the mines in Butte and the smelters in Great Falls and Anaconda relied on ample, inexpensive, and renewable hydroelectric power, making electricity out of water. Between 1902 and 1908, most of the major mining and smelting companies in Montana converted their equipment from steam to electricity. John D. Ryan, president of Anaconda Mining, began electrical generation development for the copper industry, including a hydroelectric plant at Rainbow Falls. In October of 1908, a workers' camp was established for construction of the Rainbow plant, and by mid-November, it had become a village. Because transportation to and from Great Falls was limited at best, plant workers and their families lived there year-round. It included homes, an ornate clubhouse, a swimming pool, a boarding house, office quarters, a blacksmith shop, and numerous sheds and warehouses. A rail spur to the site, as well as a temporary steam plant, came soon after. The village wood-staved water tank is still visible today, along with some of the ornamental stone walls. The original Rainbow Dam was wooden cribbing filled with rocks. It was rehabilitated in 1987 by adding concrete, a new bridge, and a rubber dam to the original structure. There are several steps to making electricity from the water contained by the dam, and we will explore them. But remember the effort and the people who built this system without the benefit of modern equipment over 100 years ago. We'll start with the forebay, where the water from the dam was regulated in a concrete cell about 164 feet long and 134 feet wide. This forebay fed two 15½ foot pipes, called flow lines, which carried water about 2,400 feet to the pressure chamber above the powerhouse. Water flow was regulated by 8 steel gates. Adjustments were cog-driven and hand-operated. An overhead gantry crane moved the trash rack cleaner, removing garbage, moss, and other trash from the flow before it entered the flow lines. In 1917, another forebay was built opposite the first one, equipped with 2 gates operated by an electric motor, much easier to move than the manual originals. They fed one 14-foot flow line, originally a wooden stave pipe that was replaced by steel in 1971. 2 surge tanks were located about 500 feet downstream of the forebay, one 55 feet in diameter and made of riveted steel plates on a concrete foundation topped by a conical wood plank roof. The other was a steel tank housed in a wood tower. One of these is an overflow, the other a pressure chamber serving as emergency regulation in case of a sudden generator shutdown. Along the east side of these towers was a wood-framed discharge chute used to channel any excess water to a culvert under the road and into the river. Both have surge chambers to regulate the flow of water to the turbines. Constructed as close to the powerhouse as possible in a sandstone bluff above it, the first chamber regulated the flow into 12 gates, feeding 8-foot steel tubes, called penstocks, which carried the water to the generator turbines. These are buried, but if you look closely, you can see them. A steel structure on top of the chamber supported the trash screens and a wooden deck. An overhead crane operated the trash cleaning rake. Pressure relief vents for each of the penstocks helped regulate the flow. In case the water level got too high, there was an overflow spillway on the northeast wall of the chamber, which ran into the Missouri River. Almost 1/2 mile from the dam was the powerhouse. This is a classic steel frame brick building with concrete floors and a concrete gabled roof. The architecture is not only very functional, but very impressive with the intricate brickwork, gabled roof, and rounded windows. Because of the high interior ceilings, the 2 levels appear to be 4 stories on the east and 3 on the west. This design was important at the time of construction as a symbol of the significance, growth, and role of industrialization. Originally built to house 6 turbine sets, 2 additional generator turbine sets were added in 1917. The quality of the construction was so good, the addition is not apparent even when you look closely. In the 1930s, a one-story brick building with similar detailing was added on the east end for equipment storage and a carpentry shop. Employees entered the powerhouse by crossing over a wood and steel footbridge built in 1931. It was put in for easy access to the generator floor. The water from the pressure pool flowed into the powerhouse beneath the floor where the 8 generators and their turbine runner pairs sat. This was a room of giant machines and incredible noise, made by General Electric generators, producing the clean, renewable, and dependable electricity we all need and use, just as they have for more than 110 years. S. Morgan Smith Company built the horizontal center discharge Francis turbine runners, and it took 2 of them to drive each generator. These are massive pieces of machinery, but they moved without any vibration, smoothly and efficiently, a testament to the skill of the people who built them and those who have maintained them. An overhead 35-ton crane rode on tracks above the generator floor, used for maintenance and installation of equipment. The water pushed the runners, which spun the generators, then discharged through steel pipes which were under the building, then into the tail race that runs beneath the bridge, and finally back into the river. On the west side of the generator floor were 15 by 18-foot pocket rooms. They held a variety of equipment: gigantic transformers, tanks for the oil that cools the turbine bearings, and storage for different equipment and parts. There was also a metal fabrication shop as well as the carpentry shop. Many of the pieces and parts that needed replacement or repair were for equipment that was so old there were no longer parts available from manufacturers. They had to be fabricated on site. These pocket rooms provided a wonderful glimpse into the inner workings of the powerhouse as well as the past. But they also showed what was asked of the employees in order to keep the powerhouse running 7 days a week, 24 hours a day. Above the generator floor was the switching center. While there was newer computer-controlled monitoring, most of what was installed in the early days still functioned and served the facility. The third level housed the unusual and seldom seen high-tension switching room. You could actually feel the amount of energy in this high-tension floor, so it was against safety rules to carry tools or anything above shoulder height. Indeed, to even lift your hands above your shoulders. Doing so could cause an arc flash, a very serious, even fatal grounding and explosion. This floor was a reality check on the amount of electricity generated in the powerhouse. The high-tension room was the last step in the generation process. The electricity went from here to the substations and lines. Outside, you could see the switch yards, substations, and overhead high-tension wires that carried the product of the powerhouse to the customers. It was very easy to get lost in the total immensity of the place, and equally easy to forget that this facility, this place of intricate brick, wood, and concrete, served just one purpose: turning water into clean, renewable, and dependable electricity. And it had been doing so continuously since 1916. It stands as a monument to those who built it and as a testament of the skill and dedication of those who maintain it. The transition from this facility represents the next chapter of electric power. Just downstream from the original powerhouse, the new powerhouse emphasizes function, is more efficient, with better security, but no less dependable, thanks to the people who work there. So the next time you turn on a light switch or appliance or television or computer, take a moment to appreciate where that energy comes from and the people who make it happen. From places like the Rainbow Dam Powerhouse, making electricity from water.